In this lab, we are analyzing the motion of a mass tied to the end of a spring, and we're comparing it to our computer model that we're going to make in VPython soon. We're also analyzing the change in energy throughout in the system throughout the movements. First, we start out with setting up our tracker. I took a calibration stick and set it to zero point 0.7 meters, which is the starting length of the spring right here. I put the origin of the coordinate plane up where the spring is hanging, so it's in the negative y direction right now. Here's what the movement looks like. Okay, so now we have to go to our VPython code and change a couple things. The mass of our object is 0.402 kilograms, and our starting position is negative 0.124 and negative 0.639. And the velocity is 0 because it starts from rest. So we move down, and gravity is 9.8, and here's where we have to find the K. Okay, so we know that the period of oscillation we can get from 2 pi times the square root of m over k. So we switch this formula around to find k. We can find the period of oscillation by looking at tracker right here. Get these and get the average period of oscillation, which ends up being 1.519 seconds. So we use these numbers to get a K of 6.878. So we put that in there, and now we have to find L0. Okay, so we know that the force of gravity will equal the force of the spring at rest. So mg equals ks. We know mg, we know k. Now we have to find s. We know that the length of the spring is 0.7 meters, so we just have to find the length at rest. So we change this formula, plug in the numbers, and get 0.27 meters. So put that in right there. Now we have to find the energies of the system. Okay, we know that kinetic energy is 1/2 times mv squared. Potential energy of gravity is mgh. The potential energy of a spring is 1/2 kx squared. So we use those and plug in these right here. So now we put in our forces. We know the force of gravity. We know the force of the spring. We know that F net is gravity plus the force of the spring. And we use Newton's second law right here to find the new velocity of the ball and to find the new position of the ball. Let's see how this runs compared to our tracker model. So you see that it follows the same path and everything. It's a little offset because of basic rounding errors, and also because the drag force caught up to the ball eventually in the real model. We can also see the graph of our energies. Now these are our kinetic, potential, spring potential, and total energies. The yellow line is the total energy, as you can see, or delta total energy. It doesn't change. Now let's look at our questions. For your model system, is the energy principle satisfied? Justify your answer by discussing briefly your plots of energy changes. As you just saw, the total energy did not change at all. So, and we know that work equals delta energy. Work on the system equals delta energy. And since delta energy is 0, there was no work done to the system. Using the data you obtained in Tracker, make 2 separate estimates of oscillation periods. First, by estimating the period of oscillation from the x position data, and second, by estimating the period of oscillation from the y position data. Well, we have these, the x coordinates and y coordinates, and the oscillation periods respectively are 1.646 and 1.519. They're different because we saw that it moves in an elliptical shape, so they don't really have to be the same. So our 2 main fundamental principles that we used today were Newton's second law and the energy principle to find the motion of an object tied to a string.